Hello, my name is Clement and I'm from the National University of Singapore. I'm here to share about our work, Shape-Haptics, planar and passive force feedback mechanisms for physical interfaces. In this research, we propose Shape-Haptics. Shape-Haptics is a new approach that enables designers to rapidly design and fabricate force feedback mechanisms for physical interfaces. Shape-Haptics mechanisms are unpowered and they can be rapidly fabricated by a laser cutter using POM sheets. These mechanisms consist of two parts, a compliance spring and a rigid profile that slides along the spring. Depending on the shape of the profile and the dimensions of the spring, Shape-Haptics mechanisms deliver variable force feedback along its travel path during interaction. Shape-Haptics mechanisms are simple, and the goal of this research is to support designers, especially industrial designers, to rapidly prototype haptics for physical interfaces, and to broaden the range of haptic expressions that these interfaces use. This work is mainly concerned with passive haptics. Passive haptic systems are unpowered and they dissipate mechanical energy during interaction to deliver force feedback. Such haptic systems are found all around us. However, despite their ubiquity, they are challenging to design as they are often made from intricate, multi-material assemblies. We are inspired by related work in HCI that leverages common materials and making processes to design passive force feedback. While these passive material systems lack the reprogrammability of an active system, they are inexpensive and easy to fabricate. In addition, material-driven haptics might also be more approachable to communities such as industrial designers, as they support exploring haptics through the lens of physical materials and making. Our material exploration led us to compliant structures fabricated from sheet materials and digital fabrication. Within HCI, researchers have used compliant structures for flexible mounts for electronics, or articulated mechanisms in personal products, or as sensing structures for 3D printed interfaces. We took inspiration from these work and directed our investigation on compliant structures towards passive haptic mechanisms. So, with that in mind, let me elaborate on the working principle of Shape-Haptics. As mentioned earlier, Shape-Haptics mechanisms consist of two parts, a side spring and a slider with a rigid edge profile. As these two parts move relative to each other, they engage and come into contact. For a specific point of contact, the magnitude of the force applied depends on the amount of compression of the spring, while the direction of the force applied depends on the angle of the profile at the contact point. Different force displacement curves can thus be generated simply by changing the shape of the sliding profile. As Shape-Haptics mechanisms move in 1 degree of freedom, they can be easily applied to support linear and rotational movements. To demonstrate how Shape-Haptics work, we fabricated 7 different mechanisms and measured their force displacement curves with a custom measurement rig. As shown here, we can achieve a variety of haptic expressions by changing the shape of the sliding profile. A big part of this research was finding and characterizing a suitable material for Shape-Haptic mechanisms so that they can work consistently and predictably. We wanted to use the laser cutter to fabricate Shape-Haptics mechanisms as it is efficient as well as available in many maker spaces. However, common laser cutter materials like acrylic or wood were not suitable candidates for compliant structures as they can be very brittle, particularly for thin geometries found in such compliant structures. Our exploration led us to POM plastic, which is already commonly used by the industry for compliant mechanisms. POM has a high tensile strength and a low coefficient of friction, making it ideal in our case. The next step after finding this material was to characterize its properties for force feedback. We began by building a parametric model of the side spring, as well as a secondary spring that's optional for Shape-Haptic mechanisms. With these parametric models, we ran FEA simulations to measure the force displacement values for different variations of the spring. We also fabricated a subset of the variations and took physical force deflection measurements. The physical measurements helped us factor for the loss of material integrity after laser cutting. These measurements gave us the spring coefficients for both springs, and they were formatted into a lookup table. We used this table for predicting the force displacement curves of Shape-Haptic mechanisms. Based on the results from our material characterization, we proceeded to develop a computational design sandbox to support other designers to explore and fabricate these mechanisms. Designers can use the sandbox to customize the sliding profile, and as that happens, the sandbox provides a real-time estimate of the mechanism's force displacement curve. Designers can interact with the virtual mechanism and see how it moves next to the FD curve. Designers can also compare different profiles and their estimated FD curves. In terms of fabrication, the sandbox generates all the necessary laser cutting files to create a swatch like the ones shown here. Alongside the pilot workshops we ran, we also engaged with the Shape-Haptics approach ourselves to develop a range of interactive applications. This process helped us to consider how designers might apply Shape-Haptics and imagine the different passive haptic expressions that the approach enables. The first set of applications we proposed are haptic attachments for existing objects and interfaces. As Shape-Haptics mechanisms are planar and easy to fabricate, they can be incorporated into existing artifacts to change their interaction haptics. For example, we attach Shape-Haptics mechanisms to a pair of pliers and a pump bottle, adding a click right when the pliers close, or steps along the pump bottle to indicate how much liquid has been dispensed. We also designed an interchangeable haptic system for VR controllers. Different Shape-Haptics profiles can be swapped in and out, changing the haptic feedback delivered when squeezing the trigger. In the third example, we designed enclosures for common electronic components. These enclosures modify and augment the haptics of these standard components. Besides the haptic attachments, we also developed a game controller. The game has only one slot for inputs, and different actions are played by swapping physical keys in and out of the slot. Each key presents a different haptic feedback through the shape of its edge profile, and we designed this haptic feedback to correspond to the specific in-game action that occurs. With this game controller, we demonstrate how a dynamic, interactive system can support different haptic feedback in a passive way. As we come to the end of this presentation, I would like to note that the approach we present here and the sandbox we developed are not without their limitations, including the narrow range of force in terms of magnitude, as well as the potential inaccuracies in estimating the force displacement curve. We discuss these limitations further in our paper. In summary, we presented Shape-Haptics, which is a new approach for designing and fabricating passive haptic mechanisms. We took multiple lines of investigation to explore materials, characterize their properties, and develop a computational design sandbox for Shape-Haptics. We also designed and fabricated different interactive applications that demonstrate its use. We hope that this work will contribute to the growing body of research in HCI surrounding how we design haptic experiences for tangible interactions. Thank you for watching this, and do reach out to us if you have any comments, questions, or feedback. We would love to hear from you, and maybe even see what you will make with Shape-Haptics.